You. Just one person on a planet with more than 8 billion inhabitants. This planet orbits a star, and that star is just one of the 100 to 400 billion stars in our galaxy alone. And our galaxy is just one among about 2 trillion galaxies in the universe. The scale of all this is honestly insane. The observable universe is 93 billion light years in diameter. But that number doesn't make any sense because we know the universe is 13.8 billion years old. So, how can it be bigger than 13.8 billion light years? It seems impossible. And it's exactly this impossibility that we're going to break down today. To try to understand the size of everything, we need to start small with ourselves. The average human being is between 1.5 and 1.8 meters tall. It's a scale we understand. Our houses, our cities, the distances we walk. It's a world made for us. Now let's take a step back. We are on the surface of the Earth, a giant sphere almost 13,000 kilometers in diameter. If you drove a car at 100 kilometers per hour without ever stopping, it would take you more than 16 days to go around the equator. That already seems huge. We feel like little ants on this vast planet. But in the grand scheme of things, our world isn't even that vast. It's just the starting line. Let's take a step outside our world. Our closest celestial neighbor is the moon. The photos make it look like it's right beside us. It's not. The average distance to the moon is 384,400 km. It's such a large number that it's hard to even visualize. So let's try it this way. You could fit 30 Earths side by side in the space between us and the moon. 30 whole worlds. The Apollo astronauts, the fastest people in history, took about 3 days to make that journey. That car of yours driving nonstop would take more than 5 months to get there. 5 months watching the Earth shrink behind you, from a blue marble sphere to a tiny dot, and we still haven't even left the cosmic garage. Now the scale really starts to get insane. Our comparison with the car doesn't work anymore. We need a new unit of measurement, the speed of light. Light travels at an absurd 300,000 kilometers per second. It takes just over a second to travel from the moon to here. So we can say that the moon is 1.3 seconds away and use this new cosmic ruler to go even farther. At the center of our solar system is the sun, about 150 million kilometers away. Light takes 8 minutes and 20 seconds to cross that distance. That means if the sun disappeared right now, we wouldn't know for more than 8 minutes. We would keep seeing it shine, feeling its warmth, completely unaware. But the solar system is much more than just the sun. The most distant planet, Neptune, orbits at an average distance of 4.5 billion kilometers from the sun. Light takes about 4 hours and 10 minutes to travel from the sun to Neptune. After that comes the Kuiper Belt, and right after, the Oort cloud, a theoretical and gigantic sphere of icy objects that marks the limit of the sun's gravitational influence. This cloud is so large that light can take from 1 to 10 years just to cross it. Light year. Almost 9.5 trillion kilometers. Our solar system is so vast that even light takes years to cross it, and we're about to discover how small that really is. Let's take a faster ship. The fastest thing humanity has ever built is the Parker Solar Probe, which reaches about 690,000 kilometers per hour. Let's point it at the star closest to our sun, Proxima Centauri, which is 4.25 light years away. How long would our fastest probe take to get there? Something like 6,700 years. Unthinkable amount of time. Entire civilizations would rise and fall, and that little probe would still be gliding through the darkness, nowhere near its destination. That's interstellar travel. The space between the stars isn't just an empty area. It's an ocean of nothing so deep that our entire solar system is just a tiny, lonely island. The distance to the next star is already absurdly large. Now let's take another step back. Our Sun and Proxima Centauri are just two stars among billions, all held together by gravity in a colossal structure. Our galaxy, the Milky Way. How many stars are in it? The best estimates range from 100 to 400 billion. Let's round it to 200 billion. For every person who has ever existed, there are at least two stars just in our galaxy. And many of them have planets. The numbers start to lose all meaning. The size? The main disk of the Milky Way is about 100,000 light-years in diameter. If our entire solar system were the size of a coin, the Milky Way would be the size of South America. That 6,700-year trip to the neighboring star, that's just a small step. When you look at the sky at night, every star you see is in our galaxy. That whitish band that crosses the sky, that's you looking at the dense and bright center of our own galaxy, seeing the combined glow of billions of stars. Our solar system is in one of the spiral arms, about 27,000 light-years from the center. We are in the galactic suburbs. The Sun takes about 250 million years to make a complete orbit around the Milky Way. The last time we were at this exact point, dinosaurs were just beginning to appear on Earth. That must be the largest scale, right? A galaxy with 200 billion stars, 100,000 light-years across. That has to be it. None of that, not even close. The Milky Way is not alone. It's part of a small cluster of galaxies called the Local Group. That includes our larger neighbor, Andromeda, about 2.5 million light-years away. And by the way, it's coming our way. Our two galaxies will collide and merge in about 4.5 billion years. Now, let's zoom out even further. The Local Group itself, which already spans millions of light-years, is just a small part of an even larger structure, the Virgo supercluster, which contains more than 100 other groups of galaxies and stretches for 110 million light-years. And even that is not the end. In 2014, astronomers discovered that the Virgo supercluster is just an arm of our true cosmic home, the Laniakea supercluster. Laniakea means immense heaven, and the name fits perfectly. It is 520 million light-years in diameter and contains about 100,000 galaxies, with a combined mass of 100 quadrillion suns. All these 100,000 galaxies, including ours, are flowing toward a single point called the Great Attractor. At this scale, entire galaxies are nothing more than specks of dust. So let's zoom out one last time. What is the universe like on the largest scale? It's not just a random jumble of galaxies. It's an intricate and magnificent network of filaments and walls of galaxies surrounding vast, almost empty regions called cosmic voids. This is the cosmic web. The superclusters are the bright nodes of this web, and the filaments are the threads that connect them. It almost looks like a brain's neural network. Now we're looking at the universe on a scale of billions of light-years. We're seeing light that has been traveling to us since before the Earth existed. And the farther we look, the further back in time we go. And that takes us to the edge, to the absolute limit of our vision. Because the universe has a finite age, there's a limit to what we can see. The light that comes from beyond a certain distance simply hasn't had enough time to reach us. That's the edge of the observable universe. And this is where we get to the number that blows your mind. The distance from us to that edge, in any direction, is about 46.5 billion light-years. That gives the observable universe a diameter of 93 billion light-years. And this is where we need to hit the brakes. I just told you two things that seem like they can't both be true at the same time. Fact 1. The universe began 13.8 billion years ago. Fact 2. The part of the universe we can see is 93 billion light-years in diameter. Wait, what do you mean? If nothing can travel faster than light, the absolute maximum distance anything could be from us is 13.8 billion light-years. The diameter shouldn't be more than 27.6 billion light-years. A diameter of 93 billion light years seems to break the most fundamental rule of physics. Was Einstein wrong? Did the Big Bang Theory fail? Is the universe much, much bigger than it seems like it should be? This is one of the biggest sources of confusion in all of cosmology. But the answer is one of the most amazing things you'll ever hear. The key is to understand what is actually expanding. It's not that the galaxies are flying through space, moving away from each other like shrapnel from a bomb. It's the very fabric of space itself that's stretching. Think of it this way. Imagine you have a really long rubber band. Draw two dots on it. One is the Milky Way, and the other is a very distant galaxy, close to the limit of what we can see. Now, an ant starts walking from the distant point to ours. This ant is a photon of light, and it always moves at the same speed. The ant starts its journey, but as it walks, we stretch the rubber band. The space between the 2 points is expanding. Our little ant keeps walking at the same constant speed, but the finish line keeps getting farther and farther away. Now apply this to the universe. 13.8 billion years ago, a photon of light was emitted by a galaxy that, at that moment, was much closer to where we are now. That photon began its long journey to us. For 13.8 billion years, it traveled at the speed of light. But during all that time, the space between our position and that galaxy was expanding. So, while the photon traveled a distance of 13.8 billion light years through space, the galaxy that sent it was carried much, much farther away from us by the expansion of space itself. Today, when that ancient photon finally reaches our telescopes, the galaxy that sent it is already an impressive 46.5 billion light years away. So, did something surpass the speed of light? No. The rule is that nothing can travel through space faster than light, but there's no limit to how fast space itself can expand. The galaxy wasn't accelerating. The universe itself was giving it a ride. What could cause an expansion of this magnitude? Scientists have a theory for this, and it's truly extraordinary: cosmic inflation. The idea is that in the very first fraction of a second after the Big Bang, a trillionth of a trillionth of a trillionth of a second, the universe went through a period of insane exponential growth. In that blink of time, a region of space smaller than an atom could have stretched to become larger than an entire galaxy. This initial hyperfast expansion boosted the growth of the universe, setting the stage for the slower expansion we see today. And it's important to remember, the observable universe is not the entire universe. It's just the part we can see. The total size might even be infinite. We've seen that the universe isn't just big. It's structured, complex, and expands in a way that defies our intuition. We live on a small planet, orbiting an average star in the suburbs of a galaxy that's just one among 100,000 in a supercluster, which in turn is just a bright spot in a vast cosmic web. We've learned that the paradox between the age of the universe and its size has a beautiful solution. Space itself is stretching. The edge of our universe isn't a wall, it's a horizon in time. But the most incredible part of this story isn't the scale. It's the fact that we can understand it. We are collections of atoms forged in the hearts of stars that died long ago, living on a little rock for a brief moment. And yet, through science, we are able to reconstruct the history of the cosmos. We look into the darkness and find our place within this great story in the making. And maybe that's the craziest and most wonderful fact of all. This entire journey from a single person to the edge of reality is a lot to process. It's a perspective that can make you feel incredibly small and at the same time part of something grand. If you found this as fascinating as I do, consider subscribing to the channel. We explore topics like this that really make you think all the time. And let me know in the comments, which cosmic mystery should we unravel next? There is a place in the universe that belongs only to you. It's not your house, it's not your city, it's a point on a ruler. And this ruler goes from the smallest length that physics has ever been able to measure to the edge of what light has had time to bring us since the beginning of everything. And here's the problem. Take this entire ruler, fold it exactly in half, and your own body falls almost right on that mark, nearly at the center of all that exists. No, that's not a figure of speech. It's not just a nice phrase to end the video. It's a calculation that any physicist can confirm on a sheet of paper in 5 minutes. And it implies something that should be impossible. You, at 5'7", are positioned between the smallest object that science can name and the largest volume of space that light has had time to cross since the beginning of everything, almost exactly in the middle of the two. Consider this scale for a moment with me. At one end, there's something called the Planck scale, a length so small that the very word space loses its meaning in there. At the other end is the edge of the observable universe, 46.5 billion light years away in any direction you look. And you, exactly you, are positioned almost halfway between the two ends. That shouldn't be possible. To find the middle of a ruler that goes from the indescribably small to the indescribably large, and discover that the midpoint lands exactly where there's a body of carbon, water, and calcium capable of making that calculation about itself? This is where it gets weird. Nobody designed this. There is no physical law that forces the observer to be born at the center of the ruler that he himself is measuring. And yet, that's exactly where you are. You are not small. You are exact. Keep that sentence in mind. It will come back piece by piece as we go down and then up this entire scale. Let's prove this calculation slowly, from your own body to the edge of everything. And to do this right, first we're going to go in the opposite direction of every video about the size of the universe you've ever seen. Before zooming out, let's zoom in, because the missing half of the story, the small half, is the one that almost no science channel takes all the way to the end. And without it, the ruler is blind on one side. You are, on average, 1 meter and 70 centimeters tall, made up of about 37 trillion cells. That number isn't simply an estimate. It's the result of a count published in 2013 by Eva Bianconi and her team in the Annals of Human Biology, who actually recalculated how many cells exist in an average adult human body, cell by tissue type. 37 trillion. More cells than stars in hundreds of galaxies combined. Each of these cells is about 10 micrometers, 0.00001 meters. That's already too small for the eye to see without help. But think about that. Inside each of those 37 trillion tiny units, there's another entire universe of structure, with its own gears, its own molecular motors, its own heavy traffic of particles going back and forth. And that's only the first floor. We still have more to see downstairs. And on that first floor, there's an old tenant you carry without even noticing. Practically every cell of yours has hundreds of mitochondria inside it, small structures whose function is to convert food into energy that the cell can use. In 1967, the American biologist Lynn Margulis published in the Journal of Theoretical Biology an article that at the time was rejected by more than a dozen scientific journals before being accepted: the theory of serial endosymbiosis. Margulis's proposal was radical for the time. Mitochondria were not born inside your cells. More than 1.5 billion years ago, they were independent bacteria living their own lives that some very ancient ancestor of complex cells swallowed and, instead of digesting, kept alive, in a partnership that continues today. Every cell in your body right now is hosting the descendant of a bacterium that decided not to be devoured. Today, the scientific community widely accepts its origin, confirmed decades later by evidence from mitochondrial DNA, which is genetically distinct from the DNA in the cell nucleus, more similar to bacteria than to the rest of you. Think about this. Part of the energy you're using to listen to this sentence right now comes from an organism that, billions of years ago, was a whole, independent creature, and that became a permanent part of almost every complex living being on the planet. Here's the first reality check. Right now, as you listen to this, Your body is replacing cells at a steady rate. Your intestinal lining replaces almost its entire cell population in just a few days. The skin you have today isn't the same skin you had a month ago. You are not a fixed object being carried through time. You are a process. And this process only makes sense on the small scale we're about to visit. And there is a physical, real clock inside each of these cells, marking how many times it can still divide. At the end of each chromosome, there are structures called telomeres, repetitive DNA sequences that work like a kind of protective cap, similar to the plastic tip of a shoelace that prevents it from fraying. In 1984, biologists Carol Greider and Elizabeth Blackburn, working at the University of California, Berkeley, discovered an enzyme called telomerase, capable of rebuilding these protective ends. And they showed that in most of the cells in your body, the telomere loses a small piece with each cell division, slowly shortening over the course of your life. Blackburn, Greider, and their collaborator Jack Szostak received the Nobel Prize in Physiology or Medicine in 2009 for this work. The exact number of divisions that a typical human cell can sustain before the telomere becomes too short varies, but it's around 40 to 60 cycles. This limit was described back in 1961 by the biologist Leonard Hayflick, even before there was a molecular explanation for it, and that's why it's called the Hayflick limit. Every time one of your 37 trillion cells divides, it's literally using up a finite and countable piece of itself. Let's go one level deeper. Inside each of your cells there are organelles, and inside the organelles there are molecules. DNA, proteins, water. A single DNA molecule, if you unraveled the strand inside just one of your cells, would measure about 2 meters long, coiled up in a structure smaller than 10 micrometers. It's like fitting 2 kilometers of thread inside a marble. The level of compaction that nature achieves at this scale has no equivalent in human engineering. The water molecule that is now inside one of your cells is about 0.275 nanometers in diameter, or 0.0000275 meters. We've already gone beyond the scale where we can visualize anything with visible light. From now on, seeing becomes a borrowed word. What scientists see at this scale are shadows of probability, reconstructed from how electrons or X-rays behave as they pass through the structure. It's not just a curiosity of scale. This is where it gets weird in a way that's worth stopping and feeling every water molecule inside you. At some point in the last billions of years, it passed through comets, ancient oceans, clouds from another planet, maybe even through the body of some animal extinct for millions of years. Water doesn't have a fixed identity, it just circulates, and you are, at this very second, a temporary stopping point in that circulation. Continuing to go deeper, inside the water molecule are the atoms, 2 hydrogen atoms and 1 oxygen atom. A single hydrogen atom has a radius of about 0.000000000053 meters or 53 picometers. At this scale, the ruler has become so small that comparing it to everyday objects doesn't help anymore. The only way to visualize it is by proportion. If an atom were the size of a room, its nucleus would be smaller than a speck of dust floating right in the center of that room. And the rest would be essentially empty space, with electrons existing as clouds of probability, not as little balls orbiting. No one knew this until 1909. Before that year, the accepted model of the atom was proposed by J.J. Thomson, the so-called plum pudding model, a uniform sphere of positive charge with negative electrons scattered inside it, like raisins in a dough. Ernest Rutherford at the University of Manchester asked 2 assistants, Hans Geiger and Ernest Marsden, to fire alpha particles. Helium nuclei, relatively heavy and positively charged, at a very thin sheet of gold, expecting that almost all of them would go straight through, maybe deflecting a little. Most of them did go straight through, as expected, but a small fraction, about 1 in 8,000. According to the measurements by Geiger and Marsden, published in 1909, and analyzed by Rutherford in 1911, they bounce back at angles greater than 90 degrees, some almost returning in the direction they came from. Rutherford later wrote a sentence that became famous in physics circles. It was like firing a cannonball at a piece of tissue paper and seeing it bounce back and hit the person who fired it. The only possible explanation was that almost all the mass of the atom and all its positive charge were concentrated in an extremely small region at the center, the nucleus, while the rest of the atom was, in practice, empty. It was like this, with gold foil and alpha particles in a room in Manchester, that humanity discovered for the first time that the solid matter we feel with our fingers is almost entirely empty. Less than 100 years before any of us were born, we would hear this phrase again, now applied to our own bodies. And it is exactly at this scale, the scale of the atom, of matter being manipulated, that we find the anchor connecting this video to the spirit of Richard Feynman. On December 29, 1959, at an annual meeting of the American Physical Society on the Caltech campus, Feynman took the Malco stage to give a lecture after dinner without any prior notes, improvised from beginning to end. According to accounts from those who were in the room that night, he titled it, "There's Plenty of Room at the Bottom." And the central argument in that room in 1959 was simple to state and gigantic. As a result, there is no law of physics that prevents humanity from manipulating atoms to build whatever it wants. Feynman calculated on the spot how many atoms would be needed to write the entire Encyclopedia Britannica on a surface the size of a pinhead, and showed that there would still be atoms left over. And a lot. The lecture was almost forgotten for more than 2 decades, and it was published in February 1960 in Caltech's own magazine, Engineering and Science. It didn't circulate much and was cited only a few times throughout the 1960s and 1970s. Only in the 1980s, when the field we now call nanotechnology began to need a respectable historical origin, did researchers return to this lecture and make it almost mythical. But Feynman didn't just leave the idea hanging. He put money on it, offering $1,000 of his own money to anyone who could build it, a functional electric motor, small enough to fit inside a cube 1/64 of an inch on each side. In November 1960, less than a year later, Quadro, a technician named William McClellan, working at Caltech, with conventional tools and a lot of manual patience, built this motor and received the prize. Feynman also offered a second prize of another $1,000 to anyone who could reduce the text of a page of a book by 25,000 times in linear scale. Small enough, in theory, to fit the entire Encyclopedia Britannica on the head of a pin. Exactly as he had calculated that night in 1959, this second challenge took much longer to be overcome. Only in 1985, a graduate student from Stanford itself, named Tom Nguyen, using an electron beam to write, managed to shrink the first paragraph of A Tale of Two Cities by Charles Dickens into an area small enough to meet the goal. And he received the second Feynman Prize, 25 years after the original challenge. Think about that. The distance between this is theoretically possible and someone actually built it with their own hands. It took less than a year for the first challenge and about 25 years for the second. This is the kind of detail that physics books usually leave out, but it shows how real science actually works. Someone makes a bet, someone builds, and the universe responds. Sometimes quickly, sometimes decades later, slower than common sense would expect, but always within what physics allows. From the beginning, let's keep going down, because the atom is still not the bottom of the well. Inside each atom, there is a nucleus, and the hydrogen nucleus, in the simplest case, is just a single proton. A proton has a radius of about 0.0000000000000000084 meters. 0.84 femtometer. Compared to the entire atom, The nucleus occupies something between a trillionth and a quadrillionth of the total volume. If the atom were the size of an entire football stadium, the nucleus would be smaller than a marble thrown in the middle of the field. This means, without any exaggeration, that you, your entire body, your 37 trillion cells, your bones, your blood, are, in terms of volume, more than 99.999999999% empty space. It's not poetry, it's nuclear geometry. The matter you feel as solid under your fingers is, on the scale of the atoms that make it up, almost entirely nothing, held together by electric forces that prevent these nothings from passing through each other. Inside the proton, there's still another level down. The proton is not an indivisible little ball. It's made up of three smaller particles called quarks, held together by another force called the strong nuclear force. Quarks, as far as experimental physics has been able to measure, have no measurable size. They behave like points with no detectable internal structure in the most powerful particle accelerators ever built, including the Large Hadron Collider, which has been operating near Geneva since 2008. And it was exactly this accelerator that, on July 4, 2012, allowed the two collaborations to announce independently of each other the detection of a particle with a mass of approximately 125 GeV, compatible with the Higgs boson, the particle theoretically predicted since 1964 by Peter Higgs, and independently by François Englert and Robert Bruch, which explains why fundamental particles like the electron and protons, and even quarks themselves, have mass, instead of traveling at the speed of light like the photon does. Higgs and Englert received the Nobel Prize in Physics in 2013 for this prediction, confirmed almost 5 decades after it was proposed on paper. This means that the mass of your body, 70 kilos, 80 kilos, whatever it is not an obvious and automatic property of matter. It is the result of a constant interaction between the particles that make you up and an invisible field that permeates all of space, including the space inside you right now. Without this field, the quarks inside your protons would have no mass at all, and nothing that you are today could exist in the solid form you recognize as a body. Here the ruler enters a territory that breaks the very question that brought it here. How big is a quark? There may not be an answer. Not because no one has measured enough, but because, as far as we know, they simply don't have an inside to measure. It's the first time on this descent that the question, what's inside here, stops making sense. But there is a theoretical last floor, even further down, and that's where the ruler truly reaches the end. It's called the Planck scale, named after Max Planck, the German physicist who, in 1900, started quantum physics by solving a problem called the ultraviolet catastrophe. The Planck length has a value of approximately 1.6 times 10 to the minus 35 meters. Written out 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 measuring distances on that scale. We're talking about something trillions of times smaller than a proton. But theoretical physics converges through independent paths on a consensus. Below that distance, the concepts of space and time as continuous lines probably stop working. Some physicists describe this as a quantum foam, a chaotic bubbling where smooth geometry no longer exists. Others suspect that space and time at this scale are emergent, arising from something more fundamental that we don't yet have a theory to properly describe. It's important to be honest here, because this channel doesn't provide easy answers where science is still debating. There is no definitive consensus about what exactly happens at the Planck scale. There are candidates, string theory, loop quantum gravity, and other approaches, but none have been experimentally confirmed. What is solid is the calculation that defines this length as the point where Einstein's general relativity and quantum mechanics together produce predictions with no physical meaning. A sign that this is the limit of our current physics, not necessarily the limit of the universe. On both sides of this theoretical dispute are real people, not abstractions. Edward Witten, a physicist from Princeton, proposed in 1995 the so-called M-theory, a mathematical structure that unifies 5 different versions of string theory that existed at the time, suggesting that space at the Planck scale could have extra dimensions, curled up so compactly that we never perceive them in our daily lives. On the other hand, the Italian physicist Carlo Rovelli, together with Lee Smolin, developed loop quantum gravity starting in the late 1980s, which proposes something even more radical: that space itself at this minimal scale is granular, made of discrete units, like pixels, instead of being a continuous and smooth surface. The two theories make predictions that are incompatible with each other, and neither of them has produced a testable prediction so far that current instruments could confirm or rule out. And here is the point that connects everything. There is nothing smaller than this that physics can describe with current tools. You went down from the human scale, meter, passing through cells, molecules, atoms, nuclei, protons, quarks, until you reached a length scale that is about 35 orders of magnitude smaller than you. This is rock bottom. This is one end of the ruler. Before turning and going back up again, it's worth a quick detour because this is where the story gets genuinely weird, not just small. You might imagine that, at the tiniest possible scale, you would finally find absolute emptiness. No particles, no fields, just total absence. Think about this. What if I told you that the most perfect vacuum physics knows is never actually empty? Quantum field theory, the theory that describes how particles and forces interact at the smallest known scales, predicts something called vacuum fluctuation. Even in the emptiest possible space with no real particles present, pairs of virtual particles constantly appear and disappear. They exist for such short fractions of time that they don't even violate the laws of energy conservation. This isn't loose speculation. It's a direct consequence of Heisenberg's uncertainty principle, formulated in 1927, applied to quantum fields instead of isolated particles. And this prediction has concrete experimental confirmation. The so-called Casimir effect, theoretically proposed by the Dutch physicist Hendrik Casimir in 1948, predicts that two metal plates placed extremely close to each other in a vacuum should feel a tiny attractive force, caused precisely by the difference in the density of quantum fluctuations between the tight space inside the plates and the open space outside them. This force was measured in the laboratory with good precision, starting in the 1990s in experiments such as those by Steve Lamoureux, then at the University of Washington, published in 1997. The quantum scale holds another peculiarity, equally well confirmed, and that changes the way you can even think about distance. In 1982, the French physicist Alain Asselin, working at the University of Paris-Sud in Orsay, conducted a series of experiments with pairs of photons emitted together, testing a mathematical inequality proposed in 1964 by the Irish physicist John Stuart Bell. The results showed that measuring the state of one photon seemed to instantly influence the state of its pair, even when the two were separated by a large distance, enough so that no signal traveling at the speed of light could have connected the two in time. Einstein called this kind of quantum mechanics prediction spooky action at a distance, and was deeply suspicious of it. Aspect's experiments refined in the following decades by teams led by Anton Zeilinger in Austria and John Clauser in the United States. Among other tests throughout the 1990s and 2000s, closing experimental loopholes that still left room for alternative explanations, repeatedly confirmed this phenomenon called quantum entanglement. Aspect, Clauser, and Zeilinger received the Nobel Prize in Physics in 2022 for decades of experimental work confirming this behavior. To this day, no one has provided a completely satisfactory explanation of exactly how this connection works. Only the repeated and increasingly precise confirmation that it exists. It's no exaggeration to say that. Nothingness, at the most fundamental scale we know, has texture, has structure, it bubbles. The word empty, which you use every day to describe a room without furniture or a glass without water, does not exist in a literal sense anywhere in the physical universe, not even in the most distant space between two galaxies. This is where it really gets weird. The concept of absolute nothingness might simply be something that physics has never encountered, because maybe it doesn't exist to be found. Now, with the small end of the ruler right in your hand, you can make the turn. Remember the ruler I promised at the start? It goes from the Planck length, 10 to the minus 35 meters, all the way to the edge of the observable universe. And to get there, we need to go back up, passing through your human scale, and keep going up without stopping until we're out of breath again, only in the opposite direction. You are here in the middle of this turn, in your body, which is 1 meter and 70 centimeters tall, made up of 37 trillion cells, each one full of atoms that are mostly empty space with quantum fluctuations happening inside all the time. It's not small. It's not big. It's a transition point between two infinities. And now the ruler will keep going up. Go up a floor. Your house, your block, your city. Go up another floor. Planet Earth, a sphere with almost 13,000 kilometers in diameter. If you drove a car at 100 kilometers per hour without ever stopping, it would take you more than 16 days just to go around the equator. It already seems immense, but compared to what's coming next, the entire Earth is still within the bounds of your everyday imagination. Take a step outside the planet. Your closest celestial neighbor is the moon, and the average distance to it is 384,400 kilometers. You could fit 30 Earths side by side in the empty space between us and it. The Apollo mission astronauts, the fastest people ever in manned space travel, took about 3 days to cover that distance. Your hypothetical car, driving nonstop, would take more than 5 months. From here on, a car is no longer a useful unit. We need a new yardstick, the speed of light. It travels at 299,792,458 meters per second in a vacuum. An exact number defined by international convention since 1983, because the meter itself started to be defined based on this speed. Moonlight takes just over a second to reach us. The sun, at an average distance of 150 million kilometers, is 8 minutes and 20 seconds away at the speed of light. If the sun disappeared right now, you would keep seeing it shine for more than 8 minutes, completely unaware of what had already happened. Neptune, the planet farthest from the sun, orbits about 4.5 billion kilometers from the sun, 4 hours and 10 minutes away at the speed of light. After it comes the Kuiper Belt, and right after that, the Oort cloud, a theoretical and gigantic sphere of icy objects that marks the limit of the sun's gravitational influence. So vast that light can take 1 to 2 years just to cross it. A light year, just for the record, is equal to almost 9.5 trillion kilometers. The entire solar system is so vast that even light needs years to cross it from end to end. It was around this region, about 6.4 billion kilometers away, that NASA's Voyager 1 probe, launched in 1977, turned its cameras back and photographed Earth on February 14, 1990. The suggestion to take this specific photo came from the astronomer Carl Sagan, who pushed NASA for years to get authorization. The engineering team feared that pointing the cameras back toward the sun could damage the probe's sensors. In the final image, Earth appears as a single pale blue pixel, occupying less than a pixel in width, suspended in a band of sunlight scattered by the camera's own lens. Sagan later described the dot as the place where every saint, every sinner, every person who ever existed had lived their entire life. I'm not going to repeat his full quote here. You can easily find it if you look for it. But the physical point still stands without needing any fancy quote. At 6.4 billion kilometers away, the entire planet, with all its wars, loves, and libraries, doesn't even occupy a single pixel in a photograph taken by the very species that lives on it. It's not A, it's not B, it's not C. It's D. It's not the planet, it's not the sun, it's not the edge of the solar system. It's the empty space between the stars that carries the true scale of the journey that remains. The fastest thing ever built by humanity, NASA's Parker Solar Probe, reaches a peak of about 690,000 kilometers per hour. That's fast enough to go from Sao Paulo to Tokyo in less than a minute. Point it toward Proxima Centauri, the closest star to the sun, 4.25 light years away. The trip would take, at the speed of our fastest probe, about 6,700 years. Entire civilizations would be born and disappear in that time, and the probe would still be gliding through the darkness, far from arriving. And this trip wouldn't be to an empty place. On August 24, 2016, a team led by the autonomous astronaut Guillem Anglades Goudet, using data from the European Southern Observatory in Chile, announced the discovery of Proxima Centauri b, a rocky planet orbiting this extremely close neighbor within the so-called habitable zone, the range of distance where liquid water could, in theory, exist on the surface. The planet has an estimated mass of at least 1.07 times that of Earth and completes a full orbit in just 11.2 days. Centauri is a small and cool star, and its habitable zone is much closer than ours. No one knows to this day if this planet really has the conditions to support any form of life. Proxima Centauri is a type of star that releases intense and unpredictable bursts of radiation, which can make the planet's surface too hostile. But the fact that there is, just 4.25 light years away, a real candidate with a mass similar to Earth's in the right temperature zone, means that the 6,700-year journey we calculated wouldn't be a trip into emptiness. It would be a journey to the neighbor's door that maybe, just maybe, has the lights on. And Proxima Centauri b isn't a rare stroke of luck. Between 2009 and 2018, NASA's Kepler Space Telescope continuously monitored the brightness of more than 150,000 stars looking for the tiny, periodic drop in light that happens when a planet crosses in front of its own star as seen from Earth. This method confirmed the existence of more than 2,600 exoplanets during the Kepler mission alone, and raised the total count of confirmed planets outside the solar system to over 5,000 today. The most solid statistical conclusion that came out of this entire survey is simple to state and enormous in its consequences. The galaxy probably has more planets than stars. Each point of light you see in the night sky, in most cases, is not alone. Our Sun and Proxima Centauri are two among a population of stars held together by gravity in a colossal structure, the Milky Way. Estimates range from 100 to 400 billion stars in this galaxy alone. Let's use 200 billion as an average reference number. For every person who has ever lived in human history, there are at least 2 stars just in our galaxy. The main disk of the Milky Way is about 100,000 light years in diameter. If the entire solar system were the size of a coin, the Milky Way would be about the size of South America. Here comes the first layer of real complication, because science at this scale doesn't settle for what the eyes see. In the 1970s, the American astronomer Vera Rubin, working with instrument specialist Kent Ford at the Department of Terrestrial Magnetism at the Carnegie Institution, measured the rotational speed of stars in several spiral galaxies, including Andromeda. Newtonian physics predicted that stars farther from the center should rotate more slowly, exactly like planets farther from the sun orbit more slowly. But the data from Rubin and Ford showed the opposite. The stars at the edges were rotating at almost the same speed as the stars near the center. Rubin and Ford published these results throughout the 1970s with a landmark paper together with Norbert Thonard in 1978 and 1980, showing that this pattern of flat rotation curves was repeated in galaxy after galaxy. The only explanation that held up was the existence of a huge amount of invisible mass spread out in a halo much larger than the visible, bright part of the galaxy, which became known as dark matter. Today, it is estimated that it accounts for about 85% of all the mass that exists in the universe. And we still don't know for sure what it is or exactly what particle it's made of. Think about that. The Milky Way you imagine, full of shining stars, is just the visible part of a much larger, invisible structure that holds it together. The galaxy you see when you look at the sky on a cloudless night is literally the visible tip of something that weighs 5 to 6 times more than it appears. And at the very center of this entire structure, there's something else that was just mathematics for decades until it became a real image. On May 12, 2022, the International Event Horizon Telescope collaboration, bringing together radio telescopes on several continents, synchronized as if they were a single Earth-sized instrument, released the first direct image of Sagittarius, A, the supermassive black hole at the center of the Milky Way, with an estimated mass of about 4.3 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. The image shows an orange ring of light around a central dark shadow. Not the black hole itself, which doesn't emit light, but the superheated gas swirling at its edge, exactly where light starts to be bent enough to never escape again. The Sun, and along with it the Earth, and along with it you, is orbiting this object about 27,000 light-years away, taking 250 million years to complete one orbit. The same number we've already seen, now with a truly visible center of gravity, photographed, not just calculated. When you look at the sky at night, every star you see belongs to our galaxy. The whitish diffuse band that crosses the sky on very dark nights is you looking straight into the dense disk of the Milky Way, seeing the combined light of billions of stars that would be individually invisible. Our solar system is located in one of the spiral arms, about 27,000 light-years from the galactic center. In the suburbs, not in the center. The Sun takes approximately 250 million years to complete one orbit around the center of the galaxy. The last time we were exactly at this point in the orbit, the first dinosaurs were just beginning to appear on Earth. Go up one more floor. The Milky Way is not alone. It is part of a small group called the Local Group, which includes our larger neighbor Andromeda, about 2.5 million light-years away. Andromeda is approaching us, and the two galaxies are expected to collide and merge in about 4.5 billion years, which is almost the same amount of time the Sun itself has existed so far. The Local Group, spanning millions of light-years, is just a fragment of something much larger, the Virgo supercluster, which brings together more than 100 other galaxy groups over a span of 110 million light-years. And even that is not the top. On September 4, 2014, a team led by astronomer Randall Brintley from the University of Hawaii, along with Helen Courtois, Yehuda Hoffman, and Daniel Pomered, published an article in the journal Nature that completely redefined the cosmic neighborhood of the Milky Way. Tully and his team didn't map the structure just by looking at where the galaxies are. They measured where the galaxies are moving. Using a catalog with more than 8,000 galaxies, they calculated the so-called peculiar velocities, which is how much each galaxy moves beyond the general expansion of the universe, pulled by local gravity. The result revealed a gigantic gravitational basin, within which the Virgo supercluster is just an arm. And they named this entire structure Laniakea, which in Hawaiian means immense sky or immeasurable horizon. Laniakea is about 520 million light-years in diameter and contains approximately 100,000 galaxies with a combined estimated mass of around 10 to the 17th power times the mass of the Sun. That's a number with 17 zeros after the 1. All these 100,000 galaxies, including ours, flow toward a region of gravitational concentration called the Great Attractor. At this scale, entire galaxies start to behave like dust particles being carried along by a current. But here's the twist that most videos about cosmic scale leave out, and that proves science is still alive, with no final answer. Studies after the 2014 paper suggest that Laniakea is probably not a gravitationally bound structure in the strict sense of physics. In other words, unlike a galaxy that stays together by its own gravity for billions of years, it's possible that Laniakea is just a temporary flow basin. And as the universe keeps expanding, this entire cosmic home may disperse and cease to exist as a recognizable unit in the distant future. The very definition of a supercluster in the gravitational sense remains an active topic of debate among cosmologists. And Laniakea isn't even the largest proposed structure. In 2014, the astronomers John Hakala, Svan Horvat, and Jut Baguli, analyzing the spatial distribution of gamma-ray bursts, some of the most energetic events ever recorded in the universe, identified a possible galaxy cluster about 10 billion light-years across, named the Hercules Corona Borealis Great Wall. If confirmed as a real structure and not a statistical sampling effect, it would be so large that it would call into question the cosmological principle itself, the central assumption of all modern cosmology that the universe is uniform on a large scale, without any special region. The scientific community remains divided on whether this structure is real or a statistical artifact of the method used to detect it. It is exactly this kind of uncertain boundary, not easy consensus, but the standard still being debated that shows this story is not closed and never has been. Go up one more floor, the last one before the edge. On even larger scales, the universe is not a random jumble of galaxies scattered by chance. It is an intricate network of filaments and walls of galaxies surrounding vast, almost empty regions called cosmic voids. Astronomers call this the cosmic web. The superclusters act as bright nodes, and the filaments are the threads that connect them, in a structure that eerily resembles a neural network. The most detailed map of this web came from the Sloan Digital Sky Survey, a survey that began operating in 2000 using a 2.5-meter telescope in New Mexico. And it has already cataloged the positions of more than 3 million galaxies and quasars, building the largest three-dimensional map of the universe ever produced by humanity. It was by looking at this map, not by relying on intuition or on an isolated theoretical model, that astronomers confirmed with statistical solidity that the structure of the cosmos is really organized in filaments and voids, and not in a random distribution. The solid observational basis on which the whole story of Laniakea and the Great Attractor rests. Now you're looking at the universe on a scale of billions of light years. The light that reaches your eyes at this distance left its origin even before the Earth existed. And the farther you look, the further back in time you're seeing. It's not a metaphor, it's physics. The physics of light propagation, period. That brings us to the edge, the absolute limit of our vision. Because the universe has a finite age, there's a point beyond which light simply hasn't had enough time to reach us. That is the edge of the observable universe. The distance to this edge in any direction you point is approximately 46.5 billion light years, which gives the observable universe a diameter of about 93 billion light years. We know that this edge is moving away because we know with confidence that space is expanding, and that certainty was born from work that began decades before anyone suspected the Big Bang. Between 1908 and 1912, the astronomer Henrietta Leavitt, working at the Harvard College Observatory, cataloged thousands of variable stars called Cephids, and she discovered a precise relationship between these stars' pulsation period and their true brightness. This gave astronomy, for the first time, a standard candle, a way to calculate the actual distance to a star just by observing the rhythm at which it pulses. Leavitt worked as a human computer at the observatory, a poorly paid and poorly recognized position at the time, without direct access to the main telescope. But it was her work that, 15 years later, allowed the astronomer Edwin Hubble, using the 2.5-meter telescope at Mount Wilson in California, to measure the distance to distant galaxies, and in 1929 published the discovery that almost all of them were moving away from us, and that the farther away the galaxy, the faster it was receding. This relationship, now called the Hubble law, was the first direct observational evidence that the universe is expanding. And even this measurement, almost a century later, still remains unresolved. Today, there are two main methods to calculate the exact speed of this expansion: the so-called Hubble constant. One of them uses supernovas and nearby stars in the local universe. The other uses the pattern imprinted on the cosmic microwave background itself, coming from the primordial universe. Both methods should, in theory, arrive at the same number, but they don't. The difference between them, now called the Hubble tension, is small in absolute terms, but statistically significant enough that it can't just be a measurement error. According to analyses published throughout the 2020s by teams like those led by Adam Rees, the same physicist who, in 1998, helped discover dark energy, no one knows for sure whether this tension reveals a hidden measurement error or if it reveals something new about the physics of the early universe that we still don't understand. It's another loose end, just like Laniakea not being gravitationally bound, just like the exact nature of dark energy. Science at this scale is still very much alive, not because there is a lack of answers, but because each new answer opens up a more precise question. One of the hypotheses proposed to explain part of this tension is particularly concrete. In 2013, the astronomers Ryan Kinnan, Amy Barger, and Lennox Coy, by analyzing the number of galaxies in different directions and distances, they identified evidence that the Milky Way may be located within a region with a lower galaxy density than the average of the universe. A kind of partial cosmic void, informally named the KBC void, with a radius of about 1 billion light-years. If confirmed, living inside a region less dense than average would make the local expansion appear slightly faster than the average expansion of the universe as a whole, which would help explain part of the discrepancy in the Hubble constant. Think about that. After this whole journey, from the Planck scale to Laniakea, from the core of the atom to the edge of the observable universe, the most recent possibility that science is testing is the very cosmic address of the Milky Way. Within the web of filaments and voids, it may be subtly distorting the ruler we're using to measure everything else. Even the position from where you measure the universe affects what you measure. And it's exactly here that we need to stop and face a contradiction that seems to break all of physics. The universe is 13.8 billion years old. The part of it that we can see is 93 billion light-years in diameter. If nothing can travel faster than light, the maximum distance anything should be from us is 13.8 billion light-years. The diameter shouldn't be more than 27.6 billion. A diameter of 93 billion light-years seems to violate the most fundamental rule that Einstein left for modern physics. Could something be wrong? Before we untangle this knot, it's worth closing the loop we opened at the beginning of this video, because this contradiction didn't come from an abstract theory. It came from an annoying radio signal that two engineers couldn't eliminate from their own equipment. In 1964, Arnold Penzias and Robert Wilson, two radio astronomers working at Bell Labs in Holmdel, New Jersey, were testing a 6-meter horn-shaped antenna originally built for communication with telecommunications satellites. When they pointed the antenna at the sky, they detected a constant uniform background noise coming from all directions in every season of the year, something that, according to the physics of the time, simply shouldn't exist. They spent months trying to eliminate this noise. They checked the electronics piece by piece. They physically cleaned the inside of the antenna after discovering that a pair of pigeons had settled inside, leaving droppings accumulated on the inner walls of the equipment, a detail that went down in the history of science precisely because it is so absurdly trivial. They removed the pigeons, cleaned everything, and the noise remained exactly the same. What Penzias and Wilson didn't know at that moment was that 60 kilometers away, at Princeton University, A team led by physicist Robert Dicke, with Jim Peebles, Peter Rowe, and David Wilkinson, was building a detector specifically to search for that same signal. The residual radiation echo predicted by the Big Bang theory cooled over billions of years until it reached a temperature just a few degrees above absolute zero. When the two groups finally exchanged information, it became clear. Penzias and Wilson had accidentally found exactly what Princeton was purposely hunting for. The two teams published articles side by side in the Astrophysical Journal in 1965. Penzias and Wilson's paper described the measurement, modest and almost timid in its title, while Dicke and the Princeton team explained its cosmological significance. The discovery came to be called the cosmic microwave background radiation, and today it is considered one of the strongest pieces of evidence supporting the entire Big Bang theory. Penzias and Wilson received the Nobel Prize in Physics in 1978 for a discovery that began as an annoying antenna maintenance problem. Their measurement in 1965 was rough, a single temperature value with no detail about variations between one direction of the sky and another. It was still necessary to map this radiation precisely. This step came with the COBE satellite, launched by NASA in 1989. In 1990, physicist John Mather and his team announced that the spectrum of the cosmic background radiation followed, with almost perfect precision, the theoretical blackbody curve. At 2.725 Kelvin, just 2.725 degrees above absolute zero, overwhelmingly confirming the original prediction of the Big Bang theory. And in 1992, physicist George Smoot, also using COBE data, announced something even more subtle. Tiny temperature variations of just a few parts in 100,000 scattered across different regions of the sky. These tiny variations are now understood as the gravitational seeds of all the structure we've discussed in this video. Without them, slightly denser here and slightly more rarefied there, no galaxy, no Milky Way, no Laniakea would ever have formed. Mater and Smoot received the Nobel Prize in Physics in 2006 for this work. The universe told you, with a precision of 1 part in 100,000, exactly where it was going to build everything that exists today, including you. The direct successor to these missions, the Planck satellite from the European Space Agency, operated between 2009 and 2013, and it refined this map to an even greater level of detail, with angular resolution about 10 times better than that of COBE. It was from the Planck data, released in successive publications between 2013 and 2018, that the scientific community arrived at the number that opened this video. 13.8 billion years with a margin of error of just a few tens of millions of years, a precision of about 0.2%. When you heard that age back at the beginning, you were hearing the result of decades of antennas, satellites, and pigeon-cleaned equipment corrections condensed into a single number. This is the loop I promised to close back at the beginning. The radiation that Penzias and Wilson found by chance in a shed full of wires and pigeon droppings in New Jersey, it's the oldest echo that humanity has ever directly detected, the closest photograph there is of the very birth of the universe. And it's precisely this radiation that carries, hidden within itself, the answer to the contradiction that opened this part of the video. The key to understanding why the community's 13.8 billion years of age matches with 93 billion light years in diameter lies in understanding what, in fact, is actually expanding. It's not the galaxies flying through space, moving away from each other like debris from an explosion. It's the very fabric of space itself that is stretching. Think of it like this. Imagine a long rubber band. Think of it with 2 points marked on it. One of them is the Milky Way. One is the Milky Way. The other is a distant galaxy near the edge of what we can see. Now an ant starts walking from the distant point to ours. This ant represents a photon of light, and it always moves at the same constant speed. The ant starts walking. But as it walks, someone stretches the rubber band. The space between the 2 points increases. The ant keeps moving at the same speed as always, but the finish line is getting farther and farther away. Apply this to the real universe. 13.8 billion years ago, a photon of light was emitted by a galaxy that, at that moment, was much closer to where the Milky Way exists today. The photon traveled at the speed of light non-stop for 13.8 billion years. But throughout this entire journey, the space between its origin and its destination was continuously expanding. As a result, while the photon traveled 13.8 billion light-years of distance through space, the galaxy that emitted it was carried away by the very expansion of space itself. Until today, it is about 46.5 billion light-years away from us. Nothing exceeded the speed of light. The rule still holds. Nothing travels through space faster than light. But there is no limit to how fast space itself can expand, because space is not something moving inside another space. It's the stage itself stretching. The galaxy wasn't running. The universe was giving it a ride. What could cause an expansion of this magnitude right at the beginning of everything? In 1980, physicist Alan Guth, then a researcher at MIT, formalized an idea he had been studying for months. After investigating why the standard Big Bang theory predicted excessive amounts of certain hypothetical particles, called magnetic monopoles, Guth realized that a mechanism capable of eliminating this excess would have the surprising side effect of driving the universe into a phase of exponential expansion, much faster than the gradual expansion we see today. Guth published the complete mathematical formalization in 1981 in an article in the journal Physical Review D titled Inflationary Universe, a Possible Solution to the Horizon and Flatness Problems. The idea became known as cosmic inflation. In the very first fraction of a second after the Big Bang, between 10 to the minus 35 and 10 to the minus 33 seconds, the universe would have expanded by an estimated factor of 10 to the 50th power, going from a region smaller than a proton to a volume comparable to a sports ball in a fraction of a second, shorter than any process the human mind can intuitively visualize. This initial hyper-rapid expansion solved all at once two problems that had troubled cosmologists. Why is the universe so uniform in temperature in opposite sides of the sky that, in theory, never had time to interact with each other? And why does the universe seem so close to flat geometry when that would require extraordinarily precise fine-tuning of the initial conditions? Inflation solves both by stretching any initial irregularity until it becomes imperceptible, just like stretching the surface of a beach ball to the size of a planet would make any local curvature appear flat. And it's not just isolated speculation. In 2014, a collaboration operating the BICP-2 telescope at the South Pole announced that they had found a polarization pattern in the cosmic microwave background radiation that seemed to confirm primordial gravitational waves predicted by inflation. That specific announcement later had to be revised. Later analyses showed that much of the signal came from dust in our own galaxy, not from the primordial universe. But the search for this direct confirmation remains one of the most active frontiers in observational cosmology to this day, with new experiments trying to refine the measurement. Remember to document this with the same scientific honesty used at the Planck scale. Cosmic inflation is the explanation that best fits the data we have and is widely accepted among cosmologists. But the exact physical mechanism that caused it, the so-called nature of the inflationary field, still doesn't have direct and complete experimental confirmation. Science advances confidently here, but doesn't claim to know everything. There is still a second layer of expansion that needs to be included in this story, because it is more recent and even more intriguing. In 1998, two teams of astronomers working independently, the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, and the HiSe Supernova Search Team, led by Brian Schmidt, with Adam Rice as the main author of the data analysis, were using Type 1a supernovae, which always explode with almost identical intrinsic brightness, as standard candles to measure cosmic distances accurately. Both teams expected to confirm that the expansion of the universe was slowing down, held back by the gravity of all the existing matter, just like a ball thrown upward slows down because of Earth's gravity. The data showed the opposite. The expansion is accelerating. The most distant supernovae were dimmer than they should have been, which means they were farther away than the predicted deceleration would allow. This result implied the existence of something that came to be called dark energy, a form of energy spread uniformly throughout space, with negative pressure, pushing the very fabric of the universe outward at an increasing rate. Current estimates indicate that it accounts for about 68% of all the mass and energy content of the universe. Perlmutter, Schmidt, and Reese received the Nobel Prize in Physics in 2011 for this discovery. And this frontier remains very much alive and still unresolved. In June 2026, a research group published a detailed reassessment of the original supernova data, correcting two small systematic errors in the measurements. And it confirmed that the 1998 discovery remains solid. The acceleration is real and began about 5 billion years ago. But what causes this dark energy still remains without a definitive explanation. Some physicists argue that it is a fixed cosmological constant embedded in the very structure of spacetime. Others suspect that it is something dynamic, which changes in intensity over cosmic time. In May 2026, mathematician Blake Temple from the University of California, Davis published an alternative model suggesting that the observed acceleration could arise from instabilities in the Einstein-Euler equations themselves, without needing to invoke any dark energy. The debate at this very moment as you hear this is still not resolved. There is another more recent confirmation that this fabric of space we talk about is not just a way to explain graphs. It can actually be felt vibrating. On September 14, 2015, the two detectors of the LIGO Observatory, separated by 3,000 kilometers between the American states of Washington and Louisiana, simultaneously recorded a tiny distortion in space itself. A gravitational wave, predicted by Einstein back in 1916, but considered for decades to be so weak that it would never be detected. The signal corresponded to the collision of two black holes, which happened 1.3 billion light-years away. With masses of about 36 and 29 times the mass of the Sun, merging into a single object of 62 solar masses. The other three solar masses were instantly converted into pure energy and radiated through space in the form of these waves. The team, led by Peter and researchers like Rainer Weiss, Kip Thorne, and Barry Barish, announced the discovery publicly in February 2016, almost a century after Einstein's original prediction. The three received the Nobel Prize in Physics in 2017. The distortion that the detectors measured at the peak of the signal was less than 1,000th of the diameter of a proton, applied to a 4-kilometer-long detection arm. It is still one of the most precise measurements ever made by any scientific instrument, and a direct, physical, tangible proof that space really behaves like a fabric, capable of vibrating. Exactly the same property that explains why it can also stretch, carrying the galaxy along with it, as we saw with the rubber band and the ant. This is where the ruler finally reaches its observable top, and where it's worth paying attention. To bring the latest chapter of this story, because it's still being written as this script was being prepared. It is seeing the past, frozen, traveling through space for more than 13.5 billion years until it finally touches the telescope's mirror. It's a very literal form of a time machine. And it is, at the current moment in science, the farthest point on the entire ruler that we are traversing. But this ruler doesn't have just two ends in space. It also has two ends in time, and we've only visited one of them so far. Looking at Mons 14 is looking at the oldest past we can reach. There's also an end in the future. And it's just as strange as anything we've seen going down to the Planck scale. In 1974, the physicist Stephen Hawking published a short article in Nature called Black Hole Explosions, in which he showed, using quantum mechanics applied to the edge of a black hole, that these objects are not eternal. They slowly emit a very weak thermal radiation, now called Hawking radiation, and over astronomically long periods of time, they lose mass until they evaporate completely. For a black hole the size of Sagittarius A, this process would take something around 10 to the power of, recorded 87 years ago, a number so much greater than the current age of the universe that comparing the two practically makes no sense. And black holes aren't the most durable objects in the long-term scenario. Experiments like the Super Kamiokande detector in Japan constantly monitor large volumes of ultra-pure water, trying to detect the spontaneous decay of protons, something that particle physics allows in some theoretical models, although it has never been directly observed. Current measurements put the average lifetime of a proton, if it decays, at more than 10 to the power of 34 years. If this prediction is correct, at some extremely distant point in the future, even ordinary matter, the atoms that make up your body, the planets, the stars, would cease to exist in the way we know today. This very long-term scenario has a name. Physicists call it the Big Freeze, or the heat death of the universe. As dark energy continues to accelerate the expansion, galaxies will move away from each other faster and faster, until the light from any galaxy, beyond our own gravitationally bound structure, can no longer ever reach us. The stars will go out one by one as they consume the available nuclear fuel. And there is no known process capable of creating more stars on a significant scale after the available gas in the universe runs out in maybe 10 to the 14 years. After that, only black holes, white dwarfs, and neutron stars remain, slowly cooling down until the final evaporation, predicted by Hawking, completes the process. It's not an exaggeration, and it's not despair. It's just the other end of the temporal ruler, symmetrical to the end we saw when looking at Malkin 14. There is a starting point, 13.8 billion years ago, where physics as we know it had not yet finished forming. And there is, in theory, an endpoint in a number of years that no everyday language can describe well, where physics as we know it will have completely dissolved into a uniform and cold silence. And there is still an idea, more speculative than the previous ones, that connects this distant end back to the beginning of everything. Alan Gaff, the physicist who formalized cosmic inflation, worked in the 2000s together with Alexander Vilenkin from Tufts University and Arvind Borg in a theorem published in 2003 showing that, under quite general conditions, inflation could not have been eternal in the past. It must have had a definite beginning. Later on in the future, the mathematics of inflation suggests the opposite, that it can be eternal, continuing indefinitely in ever more distant regions of space, creating, in theory, pocket universes separate from ours, each with its own local physics. It's important to make it clear, again, with the same honesty we applied to the Planck scale, the existence of other universes outside our own has no observational confirmation to this day, and maybe it never will, by definition. If they exist outside our cosmological horizon, no signal of light from them could ever reach us. That puts the idea closer to speculative mathematics than to testable physics. But the Borg, Goff, and Wilhelm Kahn theorem about the past, that one is a solid mathematical result, widely accepted. Only the extrapolation into the future, with multiple universes, remains at the frontier, not a consensus. Wilhelm Kahn even wrote in a popular science book published in 2006 that, if eternal inflation is correct, the number of different pocket universes, each with its own combination of physical constants, could be, in practice, unlimited. In this more extreme hypothesis, the scale that this video covered entirely, from the Planck length to the 93 billion light-years of the observable universe, would itself be just a local measurement, valid only within a single bubble, among a number, perhaps infinite, of other bubbles, each with its own physics, its own scale, and perhaps none of them with anyone inside capable of measuring anything at all. Now take that entire scale in your mind, not just in space, but also in time. From the Planck length, 10 to the minus 35 meters up to the edge of the observable universe, something around 10 to the 27 meters, taking into account the 46.5 billion light years in radius. Putting both ends together, that's more than 60 orders of magnitude in distance. An interval so vast that comparing anything else in nature to it becomes meaningless. It's not A, it's not B, it's not C, it's D. It's not the atom that marks the center of this ruler. It's not the galaxy, it's not the cosmic void, it's you. Do the math again slowly, add the exponent of the smallest known length to the exponent of the largest, divide by 2, and the result falls into a size range close to a fraction of a millimeter. But looking at the full scale of the 60-something zeros involved, your height at 1 meter 70 is at a proportionally tiny distance from this central point, much closer to it than to either of the two extreme ends. In orders of magnitude, you're not near the bottom or near the top, you're near the middle. This isn't just a philosophical coincidence created to end a nice video. It's a direct consequence of how particle physics and structure define these two ends. And from the simple fact that complex organisms like you need to be big enough to contain trillions of atoms organized in stable patterns, but small enough so that the chemical and electrical forces operating at atomic scales can still keep this organization cohesive without gravity crushing it or heat dispersing everything. You're not small, you're just right. Does this really affect your life in any way? Maybe not in tomorrow's schedule, but it does change the way you see yourself within the whole story that this video told. Every time you wash your hands, you're handling trillions of water molecules that have already passed through clouds, oceans, and maybe even through other bodies over billions of years of circulation. Every time you feel the warmth of the sun on your skin, you're receiving photons that took 8 minutes to travel 150 million kilometers through the vacuum to reach you. And every time you open the map on your phone to find an address, you're using, without realizing it, a direct correction from Einstein's general relativity. The GPS satellites orbit at an altitude of about 20,000 kilometers, where gravity is weaker. And time, according to relativity, passes slightly faster than on the surface. A difference of approximately 38 microseconds per day, adding up the effects of orbital speed and weaker gravity. It may seem negligible, but without this correction built into the system from the start, the accumulated error would make your location on the map drift from reality by about 10 kilometers per day. The cosmic scale physics that this entire video described isn't just distant theory. Right now, it's calibrating the app that takes you home. Every time you look up on a cloudless night and see that whitish band crossing the sky, you're seeing the combined light of billions of stars from our own galaxy. A galaxy that is itself just one among about 100,000 within Laniakea, which may not even be a permanent structure and could disperse over billions of future years, leaving no recognizable trace of the name we gave it in 2014. Every time you sit down to eat, you're rearranging atoms that at some point in the last 13.8 billion years passed through the interior of a star that died before the sun was born. The carbon on your plate, the calcium in your bones, the iron in your blood, none of these elements were created in the Big Bang. They were forged later inside stellar furnaces and scattered through space when those stars exploded. You don't just have an abstract cosmic origin. You have a chemical manufacturing date recorded element by element within your own body that's sitting there right now. And every time someone you love hugs you, two bodies made almost entirely of nuclear empty space, you are more than 99.9999999%. Nothing in volume. In fact, at the boundary between your skins, You are actually exchanging electromagnetic forces between clouds of electrons that never actually touch. In fact, according to the very laws of physics that govern that scale, you don't touch each other in the strictest literal sense of the word. And yet something real crosses that distance. Heat, pressure, presence. Physics doesn't diminish the gesture's meaning. It just reveals underneath it a structure that most people never get to see. I began to notice this differently after following the ruler to the end. From both ends. I no longer see a hug as a simple gesture. I see it as a meeting between two universes of almost empty space, each one carrying deep inside quantum fluctuations that never cease. And up there at the top, a connection with a web of cosmic filaments that stretches for billions of light years. I can't look in the mirror in the morning anymore without remembering that I'm looking at a scale point, not a fixed object, a specific place on a scale that goes from the unimaginably small to the unimaginably large. I also can't just hear the number 13.8 billion years as a random encyclopedia fact anymore. Behind him, there's a pair of pigeons on an antenna in New York, a woman cataloging variable stars by hand at Harvard, a technician building a microscopic engine at Caltech, and entire teams on different continents, politely disagreeing about what they still don't know. The Planck scale is still bubbling down there, out of reach of any instrument we've built so far. The edge of the observable universe keeps moving away, carried by the expansion of space itself, taking with it entire galaxies that one day may disappear from view forever. And between these two impossible-to-reach boundaries, there is you. Not at the beginning, not at the end, but exactly in the region where the two scales meet and make enough sense to produce someone capable of measuring the distance between them. You are not small. You are precisely placed. And maybe the strangest and most beautiful thing about this whole ruler isn't the size of either end. It's the fact that somewhere between the Planck length and the edge of the observable universe, matter organized itself enough to become someone capable of making this calculation about itself and finding out, with care and exact numbers, exactly where it is.